group 7, and we had activity 1. So our question was, how will changing that force of the system but keeping the net mass constant affect the acceleration of the car? And here we are testing for how the force affects the acceleration of the cart. Our hypothesis is that the acceleration of the cart will increase with the force. So we already know that the mass and the net force of the system will affect the acceleration of the object. We know that if there's no net force, there will be no acceleration, and if there is a net force, there will be an acceleration. We hope that this experiment tells us how the acceleration of the system is affected by changing the net force of the system by keeping the net mass of the system constant. We think that by increasing the force of the system, it will result in the magnitude of the acceleration increasing, and the magnitude of the acceleration would decrease if you reduce the force of the system.
Alright, so moving on to the method, the independent variable in our lab was the net force on the system, which we changed by changing the amount of mass we put on the other side of the string. And the dependent variable in our lab was the acceleration of the cart. Alright, so this is a procedure for our lab. Step 1, you must gather all of the materials, which include the lab table, the dynamics track, the cart, the sorted masses, the low friction pulley, the string, the photo gate, and then a piece of paper and something to record with. For the next step, you set up the dynamics track on the table, and also you place the cart onto the track, and then you attach one chosen mass at the other end of the string, and also you put a chosen amount of mass onto the cart. And you have one person pull the cart back until the mass at the other end of the string reaches the pulley system, and you have one person start the photo gate at the same time as the person who's holding the cart lets it go, and you have him stop the photo gate when the cart reaches the end of the track. And you record your data after this trial, but you also have to repeat for a total of 10 trials, and then each trial you don't change the amount of mass on the car, but you change the amount of mass on the other end of the string, which means you change the net force. And you record all of your data and calculate the acceleration.
The graph shows an acceleration versus net force graph. Acceleration is the y-axis and the net force is the x-axis. The net force is varied in this experiment, meaning the mass hanging down from the pulley was changed during each trial. The trend line goes across these points. As you can see, our data is really close to the trend line on the graph. But most of our points, the more net force, the higher acceleration. When there's a higher net force, you know that there's more mass hanging down and less mass on the car. We use Newton's law, F over m equals a, and when there's less mass, that means there's more acceleration in the car. If there's more mass, the acceleration will be less. For Lab 2, our claim for Activity 1 is, if the net force of the system is varied while the mass of the system is kept constant affects the acceleration of the car, then an increase in the net force, which is the hanging mass, will result in higher acceleration, and a decrease in net force will result in less acceleration. In this lab, we had many problems. For example, our string in this lab set always kept tearing or twisting, even with light weights on the mass hanging. Every time it ripped, we had to tie up the string of knots. Of course, the knots were not well made to reduce the effect on the data. In addition, since the string kept ripping, the length of the string we used became smaller over time. In this lab, we had many problems which altered the way the car is moving. For some reason, our pulley is not really tied to the ramp. Because it's not tight, the pulley is tilted during the process. For future investigations, our group would have a tool to tie to the pulley onto the ramp to prevent it from tilting. In addition, we can use new strings of the same length, prepared in case one of the strings rip or untwist. For one of the errors, we had a personal error type. We were careless and sometimes not put the mask on the car neatly or correctly. Some of the masks was just thrown on or were hanging. We could have put the mask standing up vertically. In addition, we could have systematic or measurement errors. The motion sensor was sometimes too close or too far from the car. Sometimes the motion sensor could not sense the movement of the car at all. In addition, we failed to account for some factors, such as the pulley kept tilting and may have got the car off its course, and the knots of the string could have affected acceleration as the string rolls around the pulley wheel.